Hey everybody, the video will start in just 1 second. This is just a general reminder to go visit our website at chemcomplete.com, where we offer full services such as mentoring and preparation for tests or labs. We also offer guides which you can buy, including the spectroscopy guide, which I know is of interest to most of you given that you're taking the free course on YouTube right now on how to solve for unknown organic structures using spectroscopy. We also have a free resource section where you can get a hold of some free items to help you. So go ahead and check us out at chemcomplete.com, and now onto the lesson. Alright everybody, so this is the 6th lecture in the series, and we are finally ready to break into NMR spectroscopy. So the way that I'm going to outline this is that this 6th lecture is going to be a general, and I do mean general, overview of NMR spectroscopy. I do have more detailed videos if you're interested in learning in great detail about spin-spin coupling and the splitting of peaks. If you're interested in learning about how NMR works, why chemical shift behaves the way that it does, there are videos on the channel that explain all of that. So this is going to be more of an overview of all of those details so that you have a reminder going into the C13 lecture, which will be next, and then finally into the proton lecture when we do the H1 NMR, and then we'll tie it all together at the end as we practice, and we also get ready to sort of bring together a finalized, itemized list of what we want to tackle anytime we're attempting to solve an unknown. So let's get started with this overview here. There are 2 types of NMR that are typical for solving organic structures, and that's going to be obviously carbon-13 NMR, C13 because when we're dealing with organic compounds, we're going to be certainly dealing with carbon. And then you also have proton NMR or H1 NMR, and that's because you're usually also dealing with hydrocarbons. Now, this is not to say that those are the only 2 types of NMR spectroscopy. Anytime you have an atom that has an unequal number of neutrons, you can end up with magnetic spin, and therefore you can get some sort of an NMR signal. So there's lots of different types of NMR. There's nitrogen NMR, there's fluorine NMR, there's phosphorus NMR. So I don't want you to think that carbon and the proton, the hydrogen, are the only 2 NMRs. There are additional ones, but these are the most common. So each signal on these specs, when we're looking at the spectrum, are going to represent 1 unique carbon or 1 unique hydrogen. Now, when I say 1, you could have chemically equivalent hydrogens or carbons that are all contained in 1 signal. However, every time you count one of those signals, they are each going to represent 1 unique specific type of that atom. So if I have, for instance, a carbon NMR that shows 6 carbons, that means I have 6 unique carbons. I may have more carbons than that in my structure. However, 6 of them are going to be unique from one another. Right? Now, when we deal with proton NMR, which is the H NMR, it's analyzed with coupling turned on, and that leads to peak splitting, which is when we start talking about doublets and triplets. When you see those signals split into different peaks of different heights, that is a result of coupling. And again, if you want more detail on this, you can go take a look at one of the other videos that I have. But coupling is based on magnetic signals from neighboring hydrogens. So each hydrogen has a nuclei, and that nuclei acts as its own little magnet. So let's say we have a CH3 next to a CH2. When we're looking at the signal for these 3 equivalent hydrogens, the hydrogens over here are going to influence how these protons are felt by the magnetic field, how their nuclei interact with the magnetic field. Right? So if you've got 3 of these hydrogen nuclei over here, we'll put them all in the spin up state, right? And then there's a larger, we call B naught, that's the NMR magnetic field. Then these can be influenced by the neighboring spin states. So these two hydrogen could be spin up, it could be spin up, spin down, it could be spin down, spin up, or they could both be spin down. And so because I have 1, 2, 3 different ways that they could be oriented, that makes a triplet out of the CH3, right? So we would expect this CH3 to show up as a triplet, and that's due to the influence of the neighboring potential spin patterns that we have there. And we'll talk about this in a few minutes, but that's where the N+1 rule comes from. If I have 2 neighboring hydrogens, N equals 2 plus 1 equals 3, that is a triplet that I would expect, right? Because 3 is triplet. So I could do the same thing with the CH2, assuming, let's just say there was an oxygen or something next to this. Then when I have the CH3 here, it would be 3 plus 1 equals 4, and this CH2 would be a quartet if you drew out all of those spin states. So again, check out the video on that, which I will have either linked in the description or we'll bring it up in the cards somehow. But if you're confused on what coupling and spinning is, or splitting, go ahead and check that video out. So there are 3 important factors we want to consider when we're looking at NMRs. All right. Number 1 is the chemical shift. So this is when you're looking at the x-axis, the ppm location of your signals. That's what's referred to as chemical shift. And chemical shift is actually how the peaks are moving along that ppm axis based on what's surrounding them. All right. So this will tell you whether a signal is shielded, which means it's electron rich and it's most likely near electron donating groups, or if it is deshielded and it is electron deficient and near an electron withdrawing group. So the way that this works, going back to the example we were showing above, you have B naught, which is your NMR magnetic field, and then you have your nuclei that fall into this field. So anytime there's a nuclei that is in the realm of the magnetic field, it will have electrons that are orbiting around it, right? Now this is sort of an oversimplification of the atom, but this still works for the purposes of our discussion. So when these electrons are spinning and shielding this nuclei, it doesn't feel the effects of the magnetic field as strong. And so when that's the case, you're going to end up having these nuclei shielded from the magnetic field, and their ppm is going to be lower. All right. So electrons, as we just mentioned, they act as shields for nuclei, protecting them from the NMR magnetic field. Shielded nuclei will appear upfield is the term that's used. Those are lower ppm values. So let's just use a proton NMR, for example, right? We have 0 and let's say 1 and 2. This is in the ppm scale. And then all the way up here on the higher end, we usually have about 12 ppm for a proton NMR. And when you're looking at this way is considered upfield. This would be things that are shielded by electrons. And when things become deshielded by electrons, they go downfield. If you ever get confused with this, just remember D-shield and downfield, okay, because D and D go together like that. So shielded nuclei appear upfield with lower ppm values, and deshielded nuclei will appear downfield at higher ppm values. And again, if there's an electron withdrawing group that is close to the nuclei that's going to be examined, the electron withdrawing group is taking this electron property and pulling it towards itself. That's essentially leaving the nuclei that's going to be examined here naked towards the NMR field, for lack of a better term. It's going to feel the effects of that magnetic field stronger, and therefore, in terms of the frequency and the ppm that's going to be needed, we're going to need a higher level, a higher ppm is going to be observed. It's going to be pushed downfield when the electrons are stripped away and it's deshielded. All right, so that's one important thing. And that's important because when we are presented with a spec, right, this is all sort of theoretical. But when you have a spectrum laid in front of you, whether it be proton or carbon-13, you can get a lot of information just by glancing at where the signals are appearing in terms of the ppm or the chemical shift. You want to be able to take a very quick sort of glazing over of that spectrum and be able to say, look, I see that I have things in the aromatic region. I see that I have a carbonyl. So it's very good to be able to do that first before you get into all the details about the splitting and things like that. Number 2, integration. All right, so when we deal with integration, we're talking about area under the peak. And this represents the number of identical nuclei, or the atoms those nuclei are associated with, for a given signal. So for example, when you have a proton NMR peak that integrates to 3, it means that the signal is associated with 3 identical hydrogens. Now note that I put this as likely a methyl group. Okay, you would still want to confirm that based on everything else you have as you're putting this together, but you know that most of the time if you see a peak that integrates to 3, methyls are going to come in groups of 3 like that. Right? Now, that doesn't mean that you can only have integrations of CH3, CH2, and CH, because what happens when you have a tert-butyl group where you have CH3, CH3, CH3? Well, these are CH3s, right? However, these are all chemically identical to one another when we're looking at them. And so magnetically, when we look at their spin, they're going to all appear in the same singlet area on the NMR, and therefore they will integrate to 9 when we see that. Now, if you're sitting there logically thinking about, I have an organic structure, and you come up with an integration of 9, you know that no carbon could have 9 hydrogens on it. So you have to be able to consider equivalency and what else could be there, because it is very common that you can get integrations of 9, 6, higher numbers like that. If you get to the aromatic region, you could have an integration of 5 or 4. That's the number of hydrogens found on the aromatic ring. So you have to keep in mind that it's not just methyls, methylenes, and methanes that we're dealing with. We've got other types of equivalency and functionality going on here. All right, now look at this note here. It says, many NMR programs give the raw area under the peaks, which may lead to values that do not make sense chemically. In a case like this, the peaks must be normalized to a known standard or value. So for instance, let's say that I have something like ethanol. Ethanol is going to integrate to 3 for this methyl group, 2 for the methylene here, and then 1 for the alcohol. Let's say that I have a program, and when I integrate the peaks, it ends up turning it into 33 is the area under the methyl. I'm keeping these values simple for the sake of the math here. And then 11, right? So this ratio here is still representative of a ratio of 1 to 2 to 3. And that's exactly what the area under the peak is giving you. It's giving you the ratio of the areas when you're comparing them to one another. All right, so there's a couple of techniques you can use here. You can take the lowest value and divide by it and then move forward from there. So you assume that the lowest value is always going to be associated with 1 hydrogen in that case, right? So if I divide by 11, I'd get 1, 2, and 3 back. This is a technique many teachers will tell students to use on raw data like that. The other thing that is useful is if you have some sort of an internal standard. Usually this is TMS. All right, but and TMS, by the way, is tetramethylsilane, so it's a silicon with CH3 groups on all 4 sides. This is very common. This will also show up at the 0 ppm mark when you're dealing with your NMRs if you have this present. So you know that this would be 12 hydrogens, and then you could normalize everything else based on that. So you have options on whether or not you know that you have a standard, or you can divide through by the lowest value. The other thing would be, and this doesn't apply as much if you have unknown structures, but if you do have a known structure and you know where a certain peak should be appearing, you can always adjust accordingly. Like, let's say I know that I'm looking at ethanol. I can take the methyl group if I'm sure of where its chemical shift should be, or approximately where it should be, that I can take that and I can normalize that to 3, and everything else will fall in order. So just keep that in mind when you're dealing with integration. All right, now, the last thing, and we were talking about this briefly in terms of the theory above, is splitting. Okay, so this is known as coupling of nuclei, and when neighboring atomic nuclei influence the magnetic effects of the nuclei being examined, a peak splitting will occur. So a couple of notes about this. There's the well-known n+1 rule that's implemented here, where n is the number of neighboring nuclei. Again, we mentioned that earlier. This is often turned off on carbon-13 NMR, so you'll see the term decoupled, which means that when we've got the carbon-13 NMR, we are using it just to count up the unique carbons. We're not looking at any of the type of splitting that's going on there. That tends to be reserved for the proton NMRs, the hydrogen ones. And hydrogens that are attached to heteroatoms, such as oxygen and nitrogen, will not couple or split well due to the ability to be rapidly exchanged in solution. So when you have things like OHs and NHs, okay, or maybe you have an SH, something like that, when you have these types of protons, they very readily exchange in solution. Whether it's your solvent or whether it's other molecules in your solution, it is very common for these to not have a decent splitting or coupling that is observed. So going back briefly to the example of ethanol, when I have ethanol, this right here, this OH group, the proton associated with that will appear as a singlet. And even though its neighboring carbon has the 2 hydrogens, this is due to the phenomenon that we just talked about up here, is that you've got rapid exchange with other protons, and so it doesn't really get a chance to undergo the coupling that you would see with the more stable carbon-hydrogen bonds. All right? Now, you can play around with temperature some. If you really start lowering the temperature, you slow the exchange and you can kind of bring some of the coupling back. But most of these NMRs are going to be run at an ambient temperature, meaning like room temperature. And so that's enough that you're, in general, not going to be seeing the coupling or splitting of this. So again, we already looked at this example above. You would have the triplet and the quartet for the CH3 and CH2 when you're looking at those. So what I wanted to do here was just take a look at this compound, which is ethanoic acid. And with ethanoic acid, I wanted to kind of predict or look at what we would expect here for both the carbon and the proton NMR. Now, we don't have to get into the specific ppms right now. We're going to take a look at that in the following videos. But let's take a look here. So the carbons, I've got a carbon here with the CH3. There's another carbon here for the CH2. And there's another carbon right here for the carbonyl on the carboxylic acid group. So for this compound, as far as the carbon NMR is concerned, I would expect 3 signals. And the one that I would expect to be the furthest upfield would be this CH3 right here, because the electron withdrawing group is on the other side of the chain. So it's furthest removed from that. So I would expect this to be upfield. Okay. And then I would expect this to be mid-field in comparison to the other examples here. And then this one would be furthest downfield, because that is certainly right next to the electron withdrawing effects. And again, we'll take a look at more specific examples later with the actual numbers, but this is just a brief overview here. And then for the proton, I would expect a signal from these 3, a signal from these two, and then a signal from this one. So again, I would expect 3 signals for the protons, and this is for the carbons. And let me change the color here while we're pointing this out. It would follow the same trend, right? Because we're dealing with the same molecule in terms of where I would expect things. So the up field, I would also expect for this, I would expect these to be midfield. And then this proton right here, I would certainly expect to be downfield for the hydrogen signals. All right. And again, as we look at carbon-13 and we look at proton NMR, we will end up looking at specific examples with the spectra as we start to lay that out. So that concludes the general overview. Hopefully everybody's following along here, and we will go ahead and move on to the specific examples, starting with carbon-13 in the next lecture. So remember to subscribe to be up to date all the time, and leave a like if the video was helpful. You can always leave comments and I will try to communicate and get back with you. And I would encourage you to go to our website and check us out. We do one-on-one mentoring if you have questions, you need to study for an exam. And we also have guides over there. You can buy one of our digital guides to help support the channel. And we do have one for spectroscopy. You will get the full outline along with practice. It is a huge document that takes you step by step with great detail on how to solve unknown structures using organic spectroscopy, just like we're doing in this course. So please remember to support the channel in any way possible, and of course just viewing our content helps us. And I will see everybody for the next lecture. Thanks.